moment.
Welcome to the HPC Best Practices webinar series. This series is brought to you by the IDEAS Productivity Project, which is part of the Exascale computing project of the US Department of Energy. The series is a collaboration involving the computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marquez from Lawrence Berkeley Lab. I'll be the host for today's webinar, evaluating performance portability of HPC applications and benchmarks across diverse HPC architectures. The webinar will be presented by Jae-Hyuk Kwok. Jae-Hyuk is a member of the performance engineering group at the Argonne Leadership Computing Facility, where he is responsible for ensuring the readiness of several major scientific applications on the forthcoming Aurora Exascale system. He received a bachelor and master in engineering from Seoul National University in South Korea, and a PhD in computational mechanics from the University of Illinois at Urbana-Champaign. Before joining Argonne, he worked in the Blue Waters project at the National Center for Supercomputing Applications there in Illinois. We have issued more than 200 tickets for today's webinar, and all attendees have been muted. Let's see how many people show up. People change plans and other things. We'll be receiving questions through the Zoom chat and also the Google Doc. I'll be paying attention to those. I'll paste those addresses in the chat momentarily. We have asked Jae-Hyuk to add breaks during his presentation so he can respond to questions that come in. And with that, I'll stop my sharing. Jae-Hyuk, please.
Okay, thank you, Osni, for introduction. And let me start my video and share my screen. So can you see my screen?
Yep.
Okay, great. Yeah. Okay, yeah, thanks for having me. My name is Jae-Hyuk Kwak. I'm going to talk about evaluating performance portability of HPC applications and benchmarks across diverse HPC architecture. Though I present this work was done by myself and my colleague, Colin Bertoni, Yasman Gadar, Thomas Eppercote, and Hiro Zhang, John Tram, Brian Homerding, Steve Rangel, Chris Knight, and Scott Parker. All of us made some our own contribution for this work. Okay, so today, this is a key overview of my talk today. So I'm going to talk about the HPC architecture over time very quickly. And then I'm going to share our early work for the performance study happened in 2018, 2019 timeframe. And then I will move on our most recent study, which is about performance portability on AMD and Intel and NVIDIA GPU system was done in 2021 timeframe. Okay, so I just picked several years to check what kind of HPC architecture we have. So I chose the 2015 as a petascale error. So in 2015, we have several tens of the petascale system in top 500. So in 2015 timeframe, we can see several different architecture. But if you check the data, around 15% of performance came from the GPU accelerated system in 2015 timeframe. So in this time frame, most of users are just thinking the CPU as the primary architecture, and some users use the GPU architecture for best performance. And I also chose 2018 as pre-exascale error. In 2018, we have several hundred petascale systems in top 500, including some in Sierra. So in 2018 timeframe, if we check how much performance coming from GPU, we got around 18% performance came from GPU system on the top 500 list. And then I chose 2021 as almost exascale error because last year we had a half exascale system on the top 500 list. So I would say we were not at the exascale error yet, but we are almost at the exascale error. In 2021, if we check the performance from GPU, we can see the GPU performance portion become twice more than the 3 years ago. So around 38% of performance came from GPU in 2021 timeframe. And then we are curious what happened in the exascale error, right? It will happen soon because we know several HPC centers are developing exascale system, and they will be will be deployed soon or already deployed, right? So we can get a hint from the US DOE roadmap exascale system slide, what's going on the exascale era, right? So as you see here, in 2021 to 2023 timeframe, US DOE plan to deploy several the GPU accelerated system. So for example, the Aurora system will be exascale system based on Intel GPU, and the Perlmutter Frontier will be the AMD GPU-based exascale system, and El Capitan will be another AMD-based GPU system. And we also have the very powerful pre-exascale system Perlmutter from the Berkeley lab, which is based on the NVIDIA GPU and AMD CPU. So on the exascale era, we expect more GPU accelerated system we will have, right? So, and what we are looking for. So most application developers would like to have one programming model that would run everywhere, right? So which means portability. And they want to get the decent performance across the everywhere, so which is the performance portability. And then they just want to focus on their scientific and engineering project to get some achievement, which means productivity, right? But unfortunately, I think we don't have it yet. So this talk is about our effort to explore the past and the current state of the things in terms of basic portability for the programming models, and how to evaluate performance across different architecture, and how to approach understanding the performance portability. So let me move on our first part of this talk, so which is a performance study done in 2018. In 2018 timeframe, as I showed in the previous slide, we have around 80% of performance coming from CPU-based system. So we have many different CPU. We chose the many different CPU architecture, and we also included one of the most powerful GPU in 2018 timeframe. And this work was done by me and Thomas, Colin, Yassi, Piho, and Chris and Scott, and it was presented at the Cray user group meeting early 2019. So this is the employed architecture in 2018 timeframe. So we use Intel Xeon Phi KNL processor as the kind of reference processor. So in 2018, KNL was kind of outdated architecture, but we used it as a reference. And we chose the Intel Xeon Skylake processor. It was one of the most powerful processor in 2018 timeframe. And it has 28 cores, x86 based core, and each core has 2 AVX 512 FMA units. Its vector length is 512 bit, which is very long. And the third architecture we chose was the ARM ThunderX 2 processor. So in 2018, we heard the RICAN was building ARM-based supercomputer, and now we have it. So in 2018 timeframe, we were curious about how much performance you can get from the ARM ecosystem. So we chose ARM ThunderX 2 processor as a proxy processor for that ARM ecosystem. So ARM ThunderX 2 had the same number of cores as the Skylake, so 28 cores, and each core has 2 Neon 120 vector engine. So compared to AVX, the Skylake processor, its vector length was 1/4, but the number of FMA unit and number of cores are the same, and a similar frequency. The last one was one of the most powerful GPU in 2018, so which is NVIDIA B100 GPU. And we tested, and then we used 2 ECP benchmark and 4 ECP application to check what is performance we can get. So first one is HPGMG, which is ECP proxy application, and this benchmark use full multi-grid F cycle approach. So in this diagram, you can see some typical V cycle. And the F cycle has progressively deeper V cycle to solve the problem. And to run this application on the multiple architecture, we use MPF plus OpenMP for CPU side and MPF plus CUDA for the GPU side. Neckbone is another mini app from the NEC 5000 CFD code. And in 2018 timeframe, we didn't have GPU ports, so we just used NPA plus OpenMP for the CPU, the benchmarking. And games is ECP application for quantum chemistry, and it has a lot of different complex algorithms. And in this study, we use MPI plus OpenMP for CPU and MPI plus CUDA for GPU evaluation. And LEMS is another ECP application for the molecular simulation. And for CPU, we use MPI plus OpenMP, and GPU, we use MPI plus COCOS implementation. And QMC-PEG is ECP application for electronic structure calculation. And we use the latest version in 2018 timeframe, which is QMC-PEG 3.7 with SOA optimization. We have some details later, and we use this version, and this is the input we used. And the last application is QBox, which is for the plane wave density functional theory. And this application was interesting because it used FFTW for 3D Fourier transformation and the scale effect for the parallel density linear algebra. So most of performance of this application coming from the math library. So this application is good to check how much performance you can get from the math library on the Intel system and the x86 system, and then the ARM ecosystem. So we use MKL for Skylake and KNL, and the ARM PL for Synderex2. So I don't want to go every details of each application. So I just want to show some example of how we evaluate, how we compute, how we do the performance analysis. So for HPGMG part, as I mentioned, we use 2 different ports. So FLMP port for CPU and CUDA port for GPU. And as you see here, we ran the all possible runtime configurations, so at each architecture, and then we chose the best runtime configuration for performance, right? So we didn't just run it one case and then just reported it. Instead, we tested a very different combination of runtime configuration, and then we chose the best one for each architecture. And for the input side, we also chose a wide range of input here. And then we chose the input, which we can run all the architectures, and then we could get the best performance here. So in this case, we use 512Q problem for HPGMG, and for other application, we did a similar approach. So testing multiple runtime configuration and using multiple input, and then we chose the common input, which shows best performance on the architecture. The another example is QMC-PEG here. So QMC-PEG, we measured, using this approach, we measured this data, and then we see the very big difference between Skylake and Synderex2. And then in QMC-PEG case, we also have some reference data reported by others in the 2018 timeframe. And then we also want to cross-check what we are doing correct or not, right? And it turned out the data reported by other group was totally very different from us. So they reported the difference between Skylake and Synderex2 was not 3x that much, and we could not reproduce that smaller speed up between Synderex2 and Skylake. And then we needed to the deeper analysis what's going on to check what's wrong, right? And then it turned out that we used a different version of the QMC-PEG. So in our study, we used the latest version of QMC-PEG, which is optimized through the SOA optimization. But another data was reported by the AOS-based approach, which is the previous version. And what happened here is SOA has a different memory traffic. Because of that, its performance bottleneck becomes the L1 cache bandwidth, not the memory bandwidth. Because of that, we had so we have a better performance for both cases, but we could get much better performance than Skylake because of their L1 cache bandwidths are very different to each other. So this is another example, not just running and reporting the data. We also, if possible, we also cross-checked our performance data with other data publicly available. So after this, all kind of this kind of approach, and then we measure the performance result here. So as you see here, this is the per node performance, which means if you use the same number of nodes, how much performance we could get, right? So as you see here, HPGMG and games, the LAMPs, we had CUDA port and COCOS port, so we could run on B100, but other applications, they didn't have GPU port in 2018 timeframe, so we couldn't run it on B100, so we just focused on CPU side. So as you see here, HPGMG and the games and LAMPs, B100 is always the fastest architecture we could get. And depending on the application, sometimes Skylake is very similar to whatever we have on B100. Sometimes the Skylake is even slower than KNL. So depending on the application, since they have different algorithm and their performance bottlenecks are different to each other. So we cannot easily say, oh, always B100 is 3 times better than the Skylake or something like that, right? So based on the algorithm and the architecture, we have different comparison. And then we were also curious about, this is per node performance, but the another question is each architecture uses a different power usage, right? Because of that, we are curious about how much per watt performance we could get from each architecture for each application. So in this case, we didn't measure the power usage. Instead, we just normalized performance by the TDP, thermal design power. So KNL side, we had 215 watts, Skylake 410, and ThunderX 2, 340, and V100 250. So since the Skylake and ThunderX 2 node use more power, I mean more TDP, because of that, when we normalize the performance data per power, we could see this kind of situation. So on HPGMG part, Skylake was slightly better than KNL, but since they use more power, per watt performance was less than KNL. And also difference between the KNL and the B100 becomes smaller than before, right? So this kind of thing, so we can see this kind of the variation depending on what you're looking at. So how you define your performance, the performance per watt, performance of the node, right? And the another thing we can think about is, as we know, the B100 and ThunderX TX and then Skylake and KNL, they have all different peak performance, right? They have different bandwidth, they have different plot waves. So maybe just comparing performance per node is not really a great way to compare, right? So because of that, we picked up the Roofline performance model to see the Roofline efficiency. So in Roofline model, we have x-axis, which is the arithmetic intensity. Oh, before moving on, okay, so let me stop it here. Do you have any questions?
Yeah, I have a quick question.
Yes.
If you look at these figures, you'll see that games and somewhat lamps are outsiders or somewhat different than others.
Yes.
Why is that?
That's a really good point. So from here, we see very different the behavior from the others, right? So we can talk about a little more in the Roofline analysis data. So as I mentioned, each application has different characteristics and they have different performance bottlenecks, right? So in other cases, we could say they're kind of determined by the memory bandwidth or plot wave, but the gains part we see more complex scenarios. So for example, its performance could be its performance bottleneck could be some atomic operation or some other cache performance, something like that, right? So that is our guess. So I don't know. This is answer for your question.
So there is another interesting question, I think, here.
Yeah.
So why we're discussing all the systems? Is this just to discuss the rationale behind the benchmarks? All these vendors, except for NVIDIA, have already designed their CPU and GPU architectures. The second decade belonged to NVIDIA, but it will not go their way in the third decade. Could you comment on that?
So let me try to understand the question. So the question is why we are evaluating this performance comparison across the architecture? Is it the question? Or
yeah, on all the systems. Yeah.
Yeah, so as you see on the top 500 diagram, we see the multiple hardware architecture in the HPC community, right? So so as I mentioned at the beginning, we hope to run our application on the multiple architecture with a decent performance, right? But this is kind of our early effort to understand how much decent performance we could get from the different architecture without changing further optimization. So there was one reason we are looking. We investigated the performance number from the different architectures with a similar source space. In this case, we don't use exactly the same source case because we have different source source space for the GPU and CPU yet here. But in the next part, we have the performance portability study for the same source space. I don't know if that answered for your question. Or
No, yeah, please continue. There's another question. I think the participant is still typing. Go ahead.
Okay.
Continue, please.
Okay. Thanks. Okay. So since from here we have some limitations, so we wanna go a little bit deeper in terms of the roofline efficiency, right? So roofline performance model is has two axes. One is the arithmetic intensity, which is plot by ratio, and y-axis is plot rate. And for every architecture, we have two loop lines. One is inclined loop, which represent peak memory bandwidth, and another is plateau. This is the plateau. This plateau, which represents peak plot rate. And every architecture has a transition point between the peak memory bandwidth to peak plot rate. So if your application or kernel's efficiency, plot by ratio is less than this machine balance point, you can say possibly this kernel is memory bound kernel. Otherwise, that kernel can be compute bound kernel. For memory bound kernel, we have this data. So in this case, we have measured the plot rate, which is FRK number, and then we also have measured the plot over byte ratio. So using this measured plot over byte ratio, we can estimate what could be most attainable maximum attainable performance for this kernel. So we call this is PK number. So PK, the maximum attainable performance of kernel, can be computed by the peak memory bandwidth multiplied by the arithmetic intensity in this case, or for compute bound kernel, its peak plot rate is always the peak plot rate of the architecture. So PK number is equal to peak plot rate. And then using this FRK, measured FRK, and then projected PRK number, we can compute roofline efficiency, which is FRK over PK. And this single efficiency represents two features. For memory bound kernel, this roofline efficiency is equivalent to the memory bandwidth bound efficiency. For compute bound kernel, this roofline efficiency is equivalent to plot rate efficiency. And we have, the previous the webinar about the roofline analysis. We had two webinars. So if you want more details, you can visit these two talks in IDEAS-HPC BP webinar, and you can check more details. So in order to use the roofline analysis, we measured the peak performance of each architecture using the empirical roofline toolkit. And then this is what we measured for the KNL and Dual Skylake, Dual X2, and B100. So as you see here, the KNL has around 2 teraflop per second per device. And the KNL has two different memory hierarchies. So smaller but the faster memory, which is the MCD RAM, and the larger but slower memory, which is the DRAM. And it also has the L1 cache here. And if you check the Skylake was a newer architecture than the KNL in 2018. So its maximum plot rate is around twice more than KNL. And the DRAM bandwidth is much better than KNL DRAM bandwidth, but still slower than the KNL MCD RAM. And the L1 cache bandwidth is much better than the KNL L1 cache bandwidth. And when you measure the X2, because of the shorter vector length of the X2 compared to Skylake, its peak plot rate is much lower than the KNL over Skylake. It's around 1/4 of the Skylake, right? And its memory bandwidth was slightly better than the Skylake, but the L1 cache bandwidth is much lower than Skylake. So in the previous discussion about the SOA optimization of the QMC package, the AOS performance was kind of determined by, dependent on the memory bandwidth. So the difference was not really big. But when they have SOA optimization, the performance bottleneck moves from the DRAM bandwidth to L1 cache bandwidth. Because of that, the performance we could see a very big difference between the L1 cache and the Skylake and X2. So last one is B100, which has highest plot rate, which is twice more than the Skylake, and then the fastest the HBM memory, and then the L1 cache performance is similar to B100 and Skylake. And then using this approach, we measure the performance, the Roofline data per application from the Skylake, KNL processor and Skylake processor and the Thunderx 2 processor. And then we just normalized this Roofline efficiency by the KNL to see how much variation we have, right? So since for HPG-MGFE case, since the Skylake and Thunderx 2 has a lower bandwidth in the memory compared to the MCD RAM, so because of that, its efficiency, and then the its efficiency is higher than Thunderx 2, KNL. So as a result, the Roofline efficiency-based comparison, the Thunderx Skylake and the Thunderx 2 was much better than KNL. And in the QMCPAC case, as I mentioned before, the SOA optimized version has the L1 cache bandwidth dependent of performance, right? And as a result, its DRAM-based Roofline efficiency is much higher on the Skylake processor, but much less than on the Thunderx 2. So this is a very quick summary. So in this study, we just tested the 6 benchmark applications on the 4 different types of architecture, and we measured per node performance and per watt performance and Roofline-based efficiency. And then this is kind of challenged with the portability in 2018 timeframe. So compared to now, we saw limited demand on the portability because in 2018 timeframe, we had multiple CPU vendors, which is AMD, ARM, IBM, and Intel, and so on. And in general, C++ Fortran with OpenMP were well supported by the most of vendors, including LLVM and GNU, right? And so on CPU side, we think, oh, this is mostly portable across CPU side. And then we have another species, which is the single GPU vendor, which is NVIDIA. We just have only one GPU vendor. And GPU side, NVIDIA GPU side, we had kind of 2 choices. One is the CUDA for the best performance on NVIDIA architecture, but it has no portability between the CPU and GPU. And the NVIDIA side, we had also OpenACC as a portability layer between the CPU and GPU, but we had a limited number of vendors to support this model. So we had PGI, Cray, and GNU. And we also had a portability layer from HPC community, for example, Cocos and Raja, and they had OpenMP backend and CUDA backend for CPU and GPU. But I think in 2018 timeframe, many application developers consider the CPU as the primary architecture because, as I showed at the beginning, around 82% performance came from the CPU-based system. So they consider CPU as the primary architecture, while the several developers picked the GPU for the better performance. But in this case, general approach was they just create an additional branch for the GPU because in 2018 timeframe, you just have CPU or NVIDIA GPU, right? So it's not the perfect, but it's kind of doable to manage 2 different branches, or someone use a portability layer. And then for 3 years since 2018, we see some changes and improvement. And now we see more demand on the portability. So on CPU side, we are same, right? So we have multiple vendors, and we think the portability across CPU are fine. And GPU side, now we have a multiple GPU vendor. So in addition to NVIDIA, we have AMD and Intel. And NVIDIA side, we still have CUDA with limited portability and OpenACC with limited vendor support. And now we have OpenMP target offloading support for GPUs by multiple vendors. So this is the example of vendors who support OpenMP target offloading model. We have AMD, GNU, HP, IBM, Intel, LLVM, and NVIDIA. And theoretically, if you write the OpenMP target offloading model, use OpenMP target offloading model, you can run your application on the multiple GPU systems theoretically. There is some limitation. I will discuss it later. And we also have another the newer programming model, which is SQL, led by Intel initially, and HEAP, which was led by AMD initially. And difference between the SQL and HEAP from CUDA is the SQL and HEAP are portable across the multiple GPU architecture. So we have one example in the next part. And the other change is we see increased use of the portability layer from HPC community. So Cocos and Raja are extended to support the heap and SQL backend in addition to OpenMP CUDA, like in 2018. So, and then we also see more applications are using the Cocos and Raja as their probability layer across the multiple GPU system. So now we think the more application developer consider GPU as a primary architecture. As you see in 2021 and what happened in the Exascale era, we will have a more performance from GPU accelerated system. So now people think GPU could be their primary architecture. So new challenge is how to make their application performance portable across the multiple GPU architecture. So it brings us to the next part of talk, so which is performance portability study in 2021 for AMD, Intel, and NVIDIA GPU. This work is done by me, John Tran, Colin, Yassi, Brian, Steve, and Chris Scott. So before moving on to the next part, let's pause to answer some questions. Do we have any questions?
Yeah. So there's one here. So going back to those 5 apps, those 5 benchmarks, why did you choose them?
5 different benchmarks. 6. You mean the previous benchmark here?
Yes.
Okay. So first of all, we wanted to have some real application or some proxy application to represent our ECP or DOE workload. So we cannot choose everything, but we wanna move beyond some micro benchmarking comparison. So yeah, that's one reason. And those applications are kind of these 4 applications are important applications used on our ARCF system, and also this HPG engine backbone is a good proxy to represent some CFD and continuum mechanics based the applications. It is why we chose them.
So yes, I think in summary is that some of these applications take most of the cycles in the DOE systems, right? Which is the case for electronic structure calculations, for example.
Yep.
There is another question here. It's a long one. So let's see. I may have missed this. Was a unified programming model compiler used for the benchmarks like OpenACC, OpenCL? I think you comment on that.
Yeah, so in this study, we use OpenMP for CPUs and CUDA for GPU part, and also the Cocos on the GPU part. So we didn't, yeah, that's what we used. So for the same application, we didn't use the same source space for CPU and GPU yet in this study because it was not available for every application or application. So, but yeah, there is a choice of programming model we use in this study.
Yes, please go on. There are a few other questions here, but let's wait until the end.
Okay. Okay, so next part is performance portability study done in 2018. So why performance portability on GPUs? So as I mentioned before, by moving into the Exascale era, we are expecting more accelerator-based system, right? So accelerator-based systems are one of dominant design in Exascale era. So we are gonna have new NVIDIA GPU system, which is Perlmutter, Leonardo, and Polaris. And also we are expecting new Intel GPU-based system, Aurora Argon Aurora, and the Supermug phase 2, and new AMD GPU system, which is Frontier, Capitan, and Lumi system. So it is very challenging, we think, for developers to make their application portable across HPC, these GPU-based HPC systems. And US DOE has supported 21 projects with more than 3 dozens of applications for coming Exascale systems through the ECP, Exascale Computing Project. So we want to know what is the best way to assess the application performance across the system. So in this study, we investigated performance portability of subset of ECP applications and related mini apps across AMD, Intel, and NVIDIA GPUs. So this is employed the GPU system in 2021. So all of them were publicly available in 2021 timeframe. So we chose AMD ML 100 GPU, which is a very powerful discrete GPU. And for Intel side, we use Intel Gen 9 GPU. It was a little bit outdated GPU since Intel Xe discrete GPU were not publicly available yet. So we chose this GPU as the proxy GPU for Intel, but it's a subsystem. For example, subslice and the EU architecture has some similarity to the Intel, the XE discrete GPU system. So it was good proxy. And from NVIDIA side, we chose NVIDIA A100 GPU, one of the most powerful GPU in 2021 timeframe. So yeah, again, the Intel XE brand is not publicly available. So in this study, we chose, we picked up the Intel Gen 9 GPU as a proxy GPU for Intel GPU ecosystem. ECP applications, we use the 3 ECP application for this study. So AML Wing, which is from the ECP Exa Wing project. And this application use AMReX framework as the portability layer. And the HAC application from the ECP Exascale project. So the CUDA code, the project originally has CUDA code, and that CUDA code was migrated to the SQL model through using the Intel TPCT compatibility tool. And then in this study, we just use a SQL port for 3 different GPUs. So we tested the SQL-based hack on the Intel and NVIDIA and AMD GPUs. SW4 is another ECP application from EQSIM project. And SW4 uses the Raja portability layers for Intel, NVIDIA, and AMD GPU. So we use that implementation. And we use a 3 ECP proxy application. So ECP Games Direct Mini App, which is from the Games project. And this mini app is implemented. This mini app uses OpenMP target offloading model for 3 different GPUs. And XSBench is another benchmark from OpenMC application, which is from ECP XSMR project. And XSBench has multiple ports to program models, but in this study, we picked up the OpenMP target offloading model to check the performance portability. The last mini app is a testnet, which is from LAMS application from the XSORT project. And again, the testnet also has a multiple port for 2 program models, but in this study, we just use the core-host implementation to check the performance portability. And this is our first results. So we just built them. So using the same source code, right? Same source port, and then we built and then ran the applications on 3 different GPU system, and we could run it without changing the code. So yeah, all the portability layers, which is a SQL model, OpenMP target offloading model, Focus and Raja and AMReX framework, all of them works successfully. So we could get all the green light from all the application, which is great. And then we moved on the performance portability evaluation. So there are several ways to measure the performance portability. In this study, we picked up the John Pennycook's performance portability metric, PPM. PPM is a harmonic mean of efficiency. So PPM is a good metric to represent overall efficiency across the setup platform. In this case, Intel, AMD, and NVIDIA GPU platforms. And the original paper, there were 2 recommendations for the architecture efficiency. So architecture efficiency, which is chip performance as a fraction of the peak hardware performance. And also we can use application efficiency, which is chip performance as a fraction of the best observed performance based on the most optimized implementation. And we try to use them, but we realize it is challenging to use those efficiency directly. So the reason is for architecture efficiency, we may use the peak power rate as for architecture efficiency, but it will be very restricted because from our previous study in 2018, from the Roofline analysis, we saw a lot of kernels are not just the compute bound, right? So we saw several kernels are memory bound. So if you just use peak power rate for the memory bound kernel, that efficiency could be too low. So it is too restrictive. The standard, right? And we may select several different components for the architecture efficiency, but in this case, before measuring the efficiency, we have to identify what is the major performance bottleneck for all different cases, all application, all different architecture. So that requires a lot of in-depth performance analysis. So we felt that may be too heavy at the beginning. The last one is for application efficiency, we need to implement the fully optimized kernel for each hardware platform. If we use a micro benchmark, we can do that, but for real application and the large number of applications, it's not doable. So the reason we are using portability layer is to avoid this situation, right? So this approach is not kind of doable thing we can do in this study. So in this study, we decided to use Roofline efficiency as an approximation of the architecture efficiency. So if you use that, we can say the kernels are highly performance portable if they fully utilize peak memory bandwidth or peak flop rate. So it's obviously better than using the peak flop rate, one index. But still, we may miss some other performance bottleneck, right? So through this process, we can identify some kernels which has a low Roofline efficiency, and then we can check them as that require some further investigation for performance portability, right? So, for example, memory latency dependent, critical, or something like that. So we can consider some additional index analysis for those kernels. And obviously, it does not require any optimized kernel implementation for each architecture, so it is a big plus for us. So again, before moving on, we measured the hardware, the peak performance using the empirical Roofline toolkit on Intel and AMD and NVIDIA GPU. And this is the result. So as you see, MI100 and A100, both of them are very powerful discrete GPU using very high power. So they have very high flop rates and similar to each other. And both of them use HBM2 memory, even though they have some different number of stacks. But overall, we can say, oh, they are very fast memory and similar to each other, right? Intel side, as I mentioned, we use Intel Gen 9 GPU, which is integrated GPU with a very small power usage. Because of that, its peak flop rate is much lower than others, and the peak memory bandwidth is much lower than others. But in this study, we decided to use Roofline efficiency. So at the end, we think that the efficiency-wise difference cannot be that big enough, that much. So for Roofline analysis, we needed to use the performance tool. So we need to measure some flop count and memory traffic, etc. So we need to use a different profiling tool from different vendors. So Intel side, we use Intel Advisor. So Intel Advisor has supported GPU Roofline feature for several years and a couple of years now. And it uses binary instrumentation tool, which is called GTPing. Because of that, its overhead is relatively higher than using the hardware performance counters. NVIDIA Insight started providing the Roofline feature since last year, I think. And it supports the CUDA and OpenMP target offering model. But for some reason, we can run the OpenCL application on NVIDIA GPU, but we cannot measure performance data for OpenCL based models. It's kind of weird to me, but because of that, at the beginning of this study, we had some possible OpenCL application, but we could not include that application here. So we hope NVIDIA tool will support OpenCL programming models soon. And the ROCm Profiler. ROCm Profiler is a very nice, lightweight the tool to collect performance data from hardware counters and drive the metric. MI100 GPU does not have a full set of the counters for flop. So flop cannot be measured by one or two performance counter. It is combination of the multiple counters. Because of that, because it doesn't have the full set of the counters, so we couldn't measure the flop count from the MI100 GPU. So in this study, we assume the flop count on MI100 are similar to flop count on A100 because of their similar discrete GPU. And then we hope the next generation of AMD GPU will have better situation. And I see the MI250 AMD has a different story, so we can expect better. And this is an example of how we process the performance data on multiple GPUs. So this is an example of AML Wing. So AML Wing is ECP application. So we have a lot of different kernels. So this is the screenshot from the Intel Advisor. And after running that, we chose the most time-consuming kernels because we cannot process everything for this study. So we chose 3 different kernels, which is MLA back Laplacian absolute kernel, ML Poisson absolute kernel, and ML node Laplacian absolute kernel. And then using the advisor, we measure the flower by ratio and the flop rate, and then the PK, which is the maximum attainable performance. For the same kernel, we measure the same data on the A100 GPU, like this one. And MI100, we measure the data traffic from the ROCm profiler, and we use the flop count from A100, and then we could estimate the flower by ratio and the flop rate in here. Using similar approach, we measured all the Roofline data on the 3 different architectures. So as you see here, mostly the kernels are located close to Rooflines in here. And the NVIDIA side, we have also see some consistent pattern here. And the MI100 side, we have a little bit more scattered data pattern here. The reason we guess is, as I mentioned, the MI100, the flop count was not actually measured on the MI100. That could be one reason we have some kind of big deviation. And also we see AMD SDK has evolved very, very quickly. So over time, we expect AMD side we could have a better efficiency. So anyway, this is what we measured or what we estimated. And then this is Roofline efficiency. I mean, from each kernel of the applications. And then if you just do some average value of the efficiency, we see Gen 9 has a 56% and A100, MI100 around 40%. So we cannot say from this number, we cannot say that Intel is better GPU than them, because Intel Gen 9 is much smaller GPU than other GPU in this study. So we are running same workload on different GPUs. Because of that, Intel has a better chance to get the higher occupancy or etc. Right? So yeah, that could be the reason. So we don't put a lot of pressure on here. Okay, and using the Roofline efficiency computed from measured or estimated from 3 different GPU, and we computed the PPM, performance portability metric, and using the harmonic mean, right? So and then we see the PPM is good metric. So for example, if you look at the hack geometry kernel, its PPM number is 68%. As you see here, from 3 different architecture, its Roofline efficiency is really high, right? And another case, if you look at the games arrived to mini app, we see the efficiency on 3 different GPU are relatively lower than others, and also has big variation, right? So, and then if you just check the PPM number, geometry kernel is 68% PPM, and the RM to mini app has 9% PPM. So using PPM number, we can easily check, oh, this kernel is more performance portable in terms of Roofline efficiency than this kernel, right? So in this aspect, PPM is good metric to see this information. And then we clustered those kernels in terms of the PPM number. So we just made 3 clusters. So first cluster is a high PPM number, so more than 60%. So for this kernel, we can say, oh, they are mostly performance portable in terms of the Roofline efficiency, right? For middle PPM cluster, we have a big variation here, and then we can say, oh, some are performance portable in terms of Roofline efficiency, and there's some possibility to get the benefit from further investigation, right? So this kind of the gray area here. And the last group is a low PPM cluster, which has a very low Roofline efficiency across the 3 different GPUs. So we can say they are less performance portable based on Roofline efficiency, which means their performance are not their performance bottlenecks are not memory bandwidth or cloud based, something else, right? So for this group of kernels, we need to do more investigation to identify the critical bottleneck. For example, it could be memory latency, cache performance, or uptime operation, or instruction throughput, whatever, right? So for this group of kernels, it requires some additional in-depth performance analysis to identify the performance bottleneck. So so here, there's another observation we made. So PPM number is good metric to represent performance efficiency, but in some case here, so we chose AML Wing ML node kernel, which is 35% PPM, and also Exascale kernel is 33% PPM. They are similar to each other, right? But if you look at the variation here, the AML Wing has very little variation and the Access Bench has very large variation, right? But depending on audience, we may have some different answer for this question. So can you say both kernels are similarly performance portable or not? So someone may say yes, or someone may say no. Actually, we saw different responses from our colleague as well. So for someone who don't think they are similarly performance portable, we think additional metric could be helpful to understand the consistency of the performance, right? Performance consistency. So what we did here is we just tried additional metric for performance consistency, which is can be standard deviation of average or mean or max ratio. So in this study, we just have the 3 samples per applications, right? So mean or max ratio could be good consistency metric. But if you have more sets, for example, 10 or 20 sets, maybe mean or max ratio can be polluted by the outliers, right? So in this case, we had better use the standard deviation over average approach, right? So using this consistency metric for this kernel with the same ppm number, we have different consistent metrics. So if you look at the mean or max ratio for the AML Wing case, it is a 90%, which means highly consistent with each other. And Access Bench case, it is a 37%, which is not really highly consistent with each other. So we can expect on Access Bench, we can expect more variation across the system, right? And I think this is the last part of this talk. I mean, so we also try to see the productivity, and portability layer works as an aid to productivity of the application because it can reduce or eliminate the need for multiple code branches for multiple platforms. So it's obviously positive in productivity. But we also see some challenges, even with the portability layer, nice portability layer. So one observation is architectural difference may result in the multiple branches of code. For example, Cocos is portable across CPU and GPU, but what we see in the testnet is testnet has independent code branches for CPU and GPU. The reason is GPU branch increase the number of flops with avoiding global memory read and write. So it ends up being a net benefit for the GPU platform. So this kind of architectural difference can make people to consider some additional branches, right? So this is kind of pros and cons of the in terms of productivity. And the other thing is some partially implemented programming model specification across the different platforms. So OpenMP target offloading model and SQL implemented specifications are open standard, but it does not mean all specifications are implemented at the same time by all the compilers, right? Because of that reason, developers need to understand what kind of common set are supported by the multiple compilers or multiple implementations, right? And then in order to keep their portability, they have to use that common set instead of using some specification from in the corner cases, right? So this kind of, we think this is kind of temporary issue, but I mean, our compiler implementer quickly increased the coverage of the specification, but that is what we have now. So developers need to understand the situation. Last thing is further optimization. So as I showed in the architecture difference, make some additional branches. So in order to get the best performance on specific architecture, specific platform, people may consider to make some additional branches the best performance, right? And then that just ruin the productivity. And also the performance tools interface are different from the vendor. So you need some patience to learn how to use them. So yeah, and this is a lesson we learned. So thanks to well-developed portability layer, SQL, OpenMP target offloading model, Raja, Cocos, AMR React framework, all application mini apps ran successfully on 3 different GPU systems. And getting performance data was kind of challenging. It's not impossible, but it was changing. So so we need to be patient about them to learn how to collect those data. And estimating performance efficiency was challenging, so we used Roofline efficiency, and then we could identify which kernels are memory bound or compute bound kernel easily. And then we also have some kind of third party which is not bound by compute memory bandwidth or compute block rate. So for those kernels, we can put the mark for the further performance investigation. And we also suggest the performance consistency in addition to performance portability metric to check the performance variation across the architecture. And we have some observation on performance productivity people, which I discussed in the previous slide. So this support, this work was done by the ASF and the DOE support and the Exascale computing project support. And we also use the JLC system at the Argonne National Lab for using the multiple architecture. And we appreciate our collaborators. So we have a voluntarily working group called PMA, Performance Models and Architectures, at the Argonne National Laboratory. So Abhishek and Kevin and Ye and Vitaly and Chris and Bryce, they are not authors of this talk, but they provided their technical feedback in regular basis. So we appreciate their support. And Sam Williams and Jakar for the collaboration with for the Roofline model discussion, and John, Paul, and Wei Qin for technical support for AMR Wind and AMR EX. And Rahul and Daniel for discussing about the testnet result, and then Christian and David for discussing some other performance bottleneck on the GPU side. So yeah, this is all I have. Any question?
Thank you, Jae-hyuk. Yes, we have some questions here. So let's see what we have in the chat. So just the participants, everything that came in here through the chat under the Google Doc.
Okay.
We'll ask Jae-hyuk to go through and answer. And then we'll send it to everybody that joined us today, the answer. Okay. So were any, so then going back to the questions here, were any of these test codes written in Fortran, Jae-hyuk?
That's good question. In this set of the application, we didn't use any Fortran port. So in the previous the part in 2018, the games was written in Fortran for the CPU part, right? And I know the games team is diligently working on porting the Fortran code for GPU now, but unfortunately we couldn't test it in this study. No.
All right, another question here. Let's say that a code is benchmarked as a point on the roofline plot. Mm-hmm. When the same code runs on a different machine, with will the coordinates of the point change on the roofline plot?
Yes, that's a really good question. So I mean, theoretically, we thought at the beginning, if we measure the, so in the roofline plot, there are two components are important, right? One is the plot count, another is the data traffic, right? So for plot count and for data traffic, obviously they have different data traffic because each GPU system has different size of cache, right? For example, if some GPU has very small L1 cache, and then now in this Roofline data, everything is measured from the DRAM traffic based one. So if some GPU has very small L1 traffic, that means it can have more DRAM traffic, right? If some GPU has a very large L1 cache or L2 cache, that means DRAM traffic can be reduced, right? Because of that, data traffic can be very different between the architecture. So that is something we expected. The another part, at the beginning, we thought, oh, plot count could not change because we are using exactly the same source space, right? So every case, we use the same source case. And then we thought the plot count should be exactly the same, but it was not true. The reason is we don't just use plus and we don't just use add and the multiplication, right? We have also used some math function, and the math function can be differently implemented on different architecture. So, for example, the inverse function can have different number of plots for the architecture based on the assembly, right? So, because of that reason, even the plot count can also change between the different architectures. So, yes. So, short answer is yes, depending on the architecture, your Roofline data can be moved left and right.
Let's see, another question here. Besides GPUs, are there any other accelerators going to exascale systems?
In my understanding, right now the exascale systems are using GPUs, all right? So that's my understanding. I hope to have more, but yeah, that's my understanding. Yeah.
Another question, will we get flop counts from AMD tools anytime soon?
Yeah, so actually on the ECP annual meeting happening in May, we will have the Roofline tutorial for Intel, AMD, and NVIDIA GPU side. And I know the AMD will present a new approach how to process Roofline data. And in that tutorial, you will see more details how to measure the flop count from the AMD GPUs. Yeah. So yes, in new generation, they have a better way to measure. Yeah.
So another, I think the last and short question here. There are longer questions at the top here, the Google Doc. But as I said before, Jae-hyuk will answer those in writing and will send it to everybody later. Okay, so here, where do you see standard language features playing a role in performance portability for heterogeneous systems?
So, okay, let me try to understand the question. So the question is, I mean, some newer approach from NVIDIA, the ISO compiler approach is question, not using some other portability layer.
I think that's, yeah, that's in that direction, yes.
Okay, so I saw a very nice presentation during the GTC about the ISO language for C++ support for the accelerator, which is a really nice feature. And I hope to try it out in a year time. But one of the thing is, even for the very optimal programming model, we need to have multiple supporters, right? So if only one vendor supports that programming model, for best model, for optimal model, if you don't have a multiple supporter, I don't know how many application developer will pick up that approach quickly, right? So it's related to some sustainability, right? So if you have more vendors are supporting that feature, and I believe more developers will start using those features, and then yeah, so that'll be great to see, but we'll see how it goes.
Well, I had said that was going to be the last one, but here there is another that I think is interesting and useful for this. What kind of analysis profiling tools do you think will be helpful for HPC developers to improve performance portability?
So as we present in this talk, so Roofline performance analysis could be one of the approach to identify your kernels are memory bound or the compute bound, right? But again, as I told you before, the Roofline performance data cannot capture everything, every performance bottleneck, right? So I suggest to use the Roofline performance tool as a first step of a performance analysis. After doing that, if your kernels are not bound by memory bandwidth or clock rate, you need to go to deeper analysis, which is you may need to check how much instruction throughput you have in the kernel, or how much cache bandwidth you're utilizing, or how many cache hit or miss ratio you have, right? So those kind of additional in-depth analysis are required. But as a first step, I think Roofline analysis could be a good approach to start.
All right. Okay. So thank you all for joining. Thank you, Jae-hyuk. I was just